Chapter 3 starts taking a look at graphing some specific functions. We're going to look at how we can graph polynomials, reciprocals, and rational expressions. To set this up, though, starting with the most foundational graph is a polynomial graph. We're going to first talk a bit about the shape of a polynomial graph. Now, polynomials will look something like 3x to the 4th minus 2x cubed plus 5x squared minus 7x plus 1. Or it might be, negative 3x cubed plus 7x squared plus 2x minus 5. Another example might be negative 4x to the 8th plus 3x to the 7th plus 2x squared minus 9. These are all polynomials. I want to do one more example, though. How about we do 2x to the 5th minus 3x to the 4th plus 7x squared minus 4x plus 2, something like that. The way we gauge the shape of a polynomial is we are going to have to look at the leading or largest exponent. Leading, we call it leading because it usually comes first. The leading exponent, the largest exponent, and we want to know, is it even or odd, and if it's positive or negative. And based on that fact, it's going to take one of 4 different basic shapes. 1, 2, actually let's do it this way. 1, 2, 3, 4. And how we're going to label this is going across these top 2 graphs are going to represent even leading exponents. The bottom 2 graphs are going to represent odd leading exponents. And the left side are going to represent positive, and the right side are going to represent negative. So the first graph, looking at the leading coefficient, is a positive 3. Actually, I should probably be a little more specific. Positive and negative coefficients. And even or odd is talking about the exponents. Both parts tell us something. So first, 3x to the 4th has an even exponent. Even exponent. And the coefficient 3 is positive. So that graph, what it's going to do is positive coefficients with even exponents come in from the top left, and then they're going to wiggle around in the middle. And we'll talk about the wiggle in a minute. But then they're going to leave up to the top right. A good example of this is x squared. We've seen x squared, the quadratic. It goes in from the top left and out the top right. In green here, we've got negative 3x cubed. The x cubed being odd and the coefficient being negative is going to stick us in the bottom right example. An odd negative is going to come in from the top right, wiggle around, and then go out the bottom right. An example of this would be negative x cubed. Another example here, negative 4x to the 8th is the leading coefficient. X to the 8th is even, but the coefficient is negative. And so what this graph is going to do is be a flipped version of the positive even. It's going to come in from the bottom left, wiggle around for a while, and go out the bottom right. And as you might expect, the 2x to the 5th is going to be a flipped version of the other odd one. The 2x to the 5th is going to come in from the bottom, wiggle around, and go out to the top. You should know these four shapes, basically where it comes in and where it goes out based on if it's positive or negative coefficients, and if the exponent is even or odd. I might even label this. Positive and negative is talking about the coefficient, the number in front. Even or odd, that's talking about the exponent. So that's how we determine the shape of the polynomial graph. Once we know the shape, we need to decide how it's going to wiggle in the middle. And the way we determine how it wiggles in the middle is we look at some key points. Just like when we were graphing our fundamental graphs in Chapter 2, there are key points on these polynomial functions. Now in Chapter 2, they were always the same, 0, 0, 1, 1, and a negative 1, either positive or negative 1. Here they're going to be different. They're going to be based on two things, the y-intercepts and the x-intercepts. The way we find the y-intercept is we make the other variable, make x equal to 0, and solve. The way we find the x-intercept is we make the other variable, y, equal to 0, and solve. And usually this means with the x we're going to have to factor to solve. And we're going to talk about some more factoring strategies as this unit progresses. So for example, if we're asked to graph f of x equals x plus 2 times x minus 3 times x plus 4 times x plus 1, we can find the y-intercept by making all the x's equal to 0. 0 plus 2 is 2, times 0 minus 3 is negative 3. 0 plus 4 is 4, times 0 plus 1 is 1. This gives us negative 6 times 4 is negative 24, is the y-intercept. The x-intercepts we get by making the whole thing equal to 0, and so we end up with x plus 2 equals 0, setting each factor equal to 0, x minus 3 equals 0, x plus 4 equals 0, and x plus 1 equals 0. And when I do that, I get x-intercepts of negative 2, positive 3, negative 4, and negative 1. What about the shape? We're going to multiply these x's together. When we do, we get x squared cubed fourth. And the numbers in front are always 1. 1 times 1 times 1 times 1 times 1 is 1. So we have a positive coefficient with an even exponent. Positive coefficient comes in from the top left, wiggles around, and goes out top right. So let's see if we can graph it. So our y-intercept is at negative 24, so I will just label down here negative 24, there it is. Doesn't have to be to scale. The x-intercepts are at negative 2, and 3, and negative 4, and negative 1. So we know the shape. It's going to come in from the top left. It's going to go through the first x-intercept, and then it has to bend back to the next x-intercept, bend back to the next intercept, come all the way down to the y-intercept, and back up. So this graph is going to look something like this. That's how we're going to graph our key points. Find the y-intercept, find the x-intercepts. Let's do one more example. let's graph f of x equals negative x minus 3 times x minus 1 times x minus 2. Again, the first key point is the y-intercept, where we make all the x's equal to 0. So we have negative times negative 3 times negative 1 times negative 2. For negatives, our answer is going to be positive. 3 times 1 times 2 is 6. The y-intercept is 6. To find the x-intercepts, we make the whole thing equal to 0, and because it's already factored, we can take the x minus 3 factor and make it equal to 0, x minus 1 and make it equal to 0, and x minus 2 and make it equal to 0. And so when we solve, our x-intercepts are 3, 1, and 2. For our shape, we have a negative out front times x times x times x is going to be negative x cubed. Negative x cubed, that's an odd exponent with a negative leading coefficient, so it's going to come down, wiggle, and go back out, down. So when we try and graph this, our y-intercept is at 6. 1, 2, 3, 4, 5, 6. Our x-intercepts are at 3, 1, and 2. And so we know the graph is going to come in from the top left, go through the first x-intercept, through the next x-intercept, and through the next x-intercept, and out. And this is our graph. And that's basically all there is to graphing a polynomial. When you find your intercepts, you just go through all the intercepts and wiggle around, following the shape that we would expect based on the exponents, and we get our solution. There are a couple special factors, though, I want to make sure we're aware of that do slightly different but very similar things. Two that I want to be aware of. If we have x minus a squared, or really any even exponent, the graph of this is going to do one of two things. So let's say a, that 0 is right here. When we see x minus a squared is going to hit that point twice. So it goes through it once and comes out again. It's going to bounce back down. It's coming in from the top, hits it, and bounce back for the squared. Even exponents will bounce, just like x squared does, on the x-axis. Instead of going through, it's going to bounce. Another one similar to that, if I have x minus a cubed, or really this works for any odd exponent, depending on which direction we're coming in from. Again, a is the 0. If we're coming in from the bottom, the cubed is actually going to make it level out and flatten. So instead of just going straight through, depending on which direction we're coming from, it's going to level out and flatten and then continue on through. So an example of this happening would be if f of x equals x minus 1 cubed times x plus 2 squared. The y-intercept is still very much the same. We have negative 1 cubed times 2 squared when we make all the x's equal to 0, and that comes out to negative 4. The x-intercepts, again the same way, we make it equal to 0, so x minus 1 equals 0, or x plus 2 equals 0. And so our x-intercepts are 1 and negative 2. For our shape, we've got x cubed And x squared, that's a total of x to the 5th. X to the 5th, it's positive. It's going to come in from the bottom, wiggle around, and go out the top. So let's see if that's what we get. Our y-intercept was at -4. Our x-intercepts were at 1 and -2. But the one at 1 was cubed, right? I'm going to put a little 3 next to it so I know it's cubed. And the one at -2 was squared. I'm going to put a 2 next to it so I know it's squared. Because what's going to happen is as the graph comes in from the bottom, because it's a positive 5th power, and it hits that squared, it's going to bounce back. Then it's going to come up and it's going to approach the cube, and it's going to level off because it's a cubic. Again, instead of going straight through, it leveled off at the cube. Instead of going through, it bounced at the square. That's the way we're going to have to handle those special factors. Let's do one more example. Let's do, what number am I on? 2. So let's do f of x equals x plus 3 squared times x minus 4 squared times x plus 1 cubed times x minus 1. Again, we're going to start with the y-intercept, making all the x's equal to 0. So we have 3 squared times -4 squared times 1 cubed times -1. 3 squared is 9, times -4 squared is 16. Be careful putting that negative in parentheses. Times 1 cubed times -1, that's going to be 144 negative. We then can find the x-intercept by taking each factor, making it equal to 0. X plus 3 equals 0. X minus 4 equals 0. X plus 1 equals 0. X minus 1 equals 0. You probably don't even have to write this step because you can see x is equal to -3, 4, -1, and 1. Shape-wise, we can kind of look at the squaring of the x's and the cubing of the x's. So we've got 2, 4, 5, 6, 7, 8 x's, x to the 8th, all multiplied together. The leading term is going to be a positive 1. So it's positive with an even exponent. It's going to come in from the top, wiggle, and go out the top. So let's see what this graph looks like. Y-intercept is at -144. That's down here somewhere. The x-intercepts are at -3, 4, -1, and 1. But again, I want to notice that some of these exponents, some of these intercepts had exponents on them. The -3 was squared. So we'd expect that one to bounce. I'll put a 2 for squared. The 4 was squared also. Put a 2 there on the 4. The -1 was cubed. So when we come in from the top left like we expect, when we hit our first one at -3, we should bounce. That's a squared. The next one's a cubic. It should level off. And then go down all the way to -144. Come back up at the 1. It's just a first power, so it's just going to go through, no leveling off, no bouncing. But this time when we hit the 2, we're going to bounce off the 2 and go out the top. And we have our graph. So you should be able to take any graph in factored form, any polynomial, and quickly sketch more or less what the graph looks like, knowing where it comes in, where it goes out, what the x-intercepts are, and what the y-intercepts are. Knowing when to go through an intercept, when to bounce, and when to level off. We can also do the same exact process backwards. I can give you the graph and ask you to give me the equation. And again, the information that we're interested in is the same information, the intercepts, which are going to derive our entire result. Let's start with a simple example. Let's take a graph that comes in, goes through this point, bends back, goes through that point, and bends back and goes through that point. The y-intercept, you see, is at 1. We're going to come back to the y-intercept. What's going to be interesting to us as we start to build the equation that this graph goes with is we start with the x-intercepts. X equals -2, x equals -1, and x equals +1. Remember, those x-intercepts came off of finding our factors that were equal to 0. So we want to make these equations equal 0. The first one we add 2, and we get x plus 2 equals 0. That's one of our factors. The next one we add 1, and we get x plus 1 equals 0. There's another factor. The next one we subtract 1, and we get x minus 1 equals 0. And so we use those factors of x plus 2 times x plus 1 times x minus 1 to start to build our polynomials. Now there's a little bit of a catch. We can't just say y equals and be done, because we haven't yet used the y-intercept. There could be, and in fact most of the time there is, some number, we're going to call it a, in front of all these factors. And the only way to find that a is to use another point on the graph, usually the y-intercept. So here the y-intercept is 1, so y equals 1 when x is equal to 0. We don't know what a is, but if x is 0, we have times 2 times 1 times -1. Or cleaning it up, -2a is equal to 1. Solving for a is quite simple. We divide by the -2, and a must be -1/2. And so we can see then our entire function is y equals that a, the -1/2, times x plus 2 times x plus 1 times x minus 1. We now have our polynomial. Let's do another example that's probably a little more interesting to this to wrap up. So if we call that example 1, this next one we're going to call example 2. So this one's going to come in, we're going to bounce, come up, go through, come up, and then we're going to level off as we go through there. And we're going to come up with the equation, the function, for this graph. Well, you'll notice the first is the y-intercept is at 2, but remember we're going to care more about that at the end when we try and figure out what a is. The x-intercepts, we've got an x-intercept at -1. But notice it bounced. Because it bounced at that point, what's going to be special about this factor? This factor is going to be squared. So when we add 1 to both sides, we get x plus 1 equals 0, but that factor should be squared to create the bounce. The next x-intercept is at x equals 1. It just goes through that point, so we'll subtract 1. Nothing fancy, x minus 1 is our next factor. Our third x-intercept at x equals 4, though, is interesting because you notice the graph levels off. It doesn't just go through it like the intercept in the middle did. Because it levels off, we know we're probably going to need to cube this factor. So when we subtract 4 and say it equals 0, we also need to make sure that factor is cubed to give us that illusion of leveling off. So the first is x plus 1 squared, then we had an x minus 1, and then we had our x minus 4 cubed. And again, we'll say y equals a times all of that, because we need to figure out if there's a number in front. Usually there is, and we can calculate that from our y-intercept. Our y-intercept is 2, so we'll say 2 equals, and we'll make all the x's equal to 0. So we have a times 1 squared times negative 1 times negative 4 cubed. So 2 equals, 1 squared is 1, negative 4 cubed is negative 64, times negative 1 is positive 64a. Divide both sides by 64, and a is 1 over 32. So our final function, this graph that we have drawn in front of us here, is 1 over 32 times x plus 1 squared times x minus 1 times x minus 4 cubed. Again, on today's assignment, we're just getting that basic pattern of what these polynomial graphs look like. You should be able to find the y-intercept. You should be able to find the x-intercept and decide, is it going to go through it? Is it going to bounce because of an even exponent? Or is it going to level off because of an odd exponent? In addition, you should know the general shape of every polynomial based on if it's even or odd exponents and whether the coefficient is positive or negative. You should know where it comes in and where it goes out. Take a look at the homework and practice a few of these. These are really easy and go fast once you get it. Takes a little bit to get it, though, but once you get that pattern down, every problem essentially the same. So good luck on the homework. We will see you in class tomorrow.